Good afternoon, everyone. I am Mehdi Afshar from Hamburg University of Technology, and today I am here to present our recent work related to assessment of combined impact of climate change and land cover alternations on soil degradation. So I think after today's talk, there is no need for me to talk about the motivation and the importance of soil health and negative impacts of soil degradation on it, and I can directly talk about our objective, which is using AI modeling framework to enhance our understandings about soil degradation and also predict future dynamics of it under different climate change and land cover alternations. So here is our framework. We used AI modeling to link different soil health drivers coming from soil inherent properties, climate factors, and land cover fractions. And we linked these variables to soil degradation intensity. And after training and validating our AI models, we used the developed models to predict the future change in soil degradation based on future projections of variables we considered in our model development phase. So for the target variable of our AI models, we use our recently developed soil vulnerability index that quantifies soil degradation intensity using soil erosion rate, electrical conductivity, pH, and organic carbon to capture different aspects of physical, chemical, and biological degradation. And to calculate soil vulnerability index, we initially retrieved these factors using Lucas observations and later rescaled them to the scale of 0 and 1, and then got the average values of these components to reach to a continuous scale of soil degradation intensity varying between 0 and 1. And how do we rescale these values? Very similar to what we heard today earlier related to external benchmarking and using distributions. We also followed the CDF of variables we considered in soil vulnerability index development. Namely, for erosion rate and electrical conductivity, we considered a positive relationship, meaning that with increasing erosion rate and also electrical conductivity, the soil vulnerability index also increases. And for soil pH, we considered two-way relationship with putting soil pH equal to 6.5 as optimum value for soil health conditions, and going toward left and right, our soil vulnerability index also increases. For soil organic carbon, we considered inverse relationship, meaning that in our methodology, healthier soil contain more soil organic carbon. And considering all of these methodologies, we reached to soil vulnerability index map shown on the left side, a continuous measure of soil degradation intensity varying between 0 and 1. Values closer to 1 showing unhealthier soils represented by reddish colors, and lower values of SVI are showing the healthier condition in soils. In the middle panel, you can see the variation of SVI over different land covers and soil textures. And looking to that, we can see, for example, forest lands are generally contain lower SVI when you compare it with croplands. And comparing the map in the left with two maps on the right, which are the available soil degradation maps in the literature, we can see a really good consistency between them, with this difference that soil vulnerability index benefits from two main advantages of being first continuous and also contain less subjective decisions about converting soil health indicator maps to binary maps of healthy and unhealthy soils. And to get a better understanding about the soil vulnerability index, we calculated SVI for both years 2015 and 2018 using Lucas observations. And then we went to use Google imageries and see how SVI changed for some particular points. Looking to the Google imageries in the left, you can see a point that had SVI value of 0.41 in the left, and within 3 years, the SVI reached to 0.87 because of land cover alternations. And on the right-hand side, you can see the inverse relationship going from higher SVI to healthier conditions by changing, I guess, croplands to tree cover. We also did this analysis in space. We considered 4 main land cover types in Lucas observations: cropland, grassland, shrublands, and forestland. And in the top row, you can see the different locations of Lucas observations with SVI values close to 0. And in bottom row, the same cropland, but SVI value closer to 1. And as an example, you can see, for example, over forest lands, SVI close to 0 has denser vegetation cover. And when we got sure about the variation of SVI across different land cover types, we went toward the next step and tried to use AI framework to develop models and also predict the future dynamics of soil health conditions in Europe. So to do that, we considered 23 global climate models under 2 shared socioeconomic pathways of 2, 4.5 and 5, 8.5, with considering 2 time periods of near future and far future. On the right-hand side, you can see the performance of our developed model with R-squared values close to 0.58 and mean square error close to 0.01, which shows the accuracy of our model in predicting SVI values. So to develop the AI models, we use different environmental variables. And in this figure, I tried to show the variable importance of different models. And looking to this, we can understand that not only land cover type plays a key role, but also land management practices, and after them, air temperature gets the key role in predicting a soil vulnerability index. And one of the main outcomes of our analysis was related to comparison of future SVI values with historical ones. On the left side, you can see a historical map of SVI. In the middle panel, you can see the expected change in future with 2 socioeconomic pathways condition and also 2 time periods of near future and far future. And on the right-hand side, you can see the average SVI difference across different latitudes. And paying attention to average change according to the latitudes, you can see that we expect to see the higher change in Northern Europe, particularly around latitude equal to 60 degrees. And when you look at the maps, you can also see the same pattern that countries like Sweden, Finland, or Estonia in Northern Europe are expected to face with heightened soil vulnerability index and going toward unhealthier soils. And on the other hand, countries like Spain or Italy, which traditionally had higher SVI values, are expected to go toward healthier soils. And here the question comes that what is the driver of this change? Was it because of climate change or land cover alternations? And to answer that question, we run also 2 isolated scenarios with considering only change in climate and also change in only in land cover types. And when we compare these maps, we can see mostly orangish colors in northern countries, which is related to the category of positive change in SVI related to climate change, meaning that the heightened SVI values are expected to happen according to the change in climate, and the going toward healthier soils in southern regions are mostly linked to land cover alternations. And when we compare the frequency of these categories we considered as a driver of change in SVI, we can see that we're going from near future to the far future under SSP 5.8.5, the frequency of negative change in soil health conditions based on climate change also increases. So my last slide, we also did a relative frequency analysis of drivers of change in SVI according to different land cover types and climate zones. And we found out that mostly the forest lands and cold climate zones are expected to face with heightened SVI values, where the arid zones are expected to go toward healthier soils according to the land cover alternations. And as a summary, I wanted to say that Europe is expected to face with significant change in soil vulnerability, especially under SSP 5.8.5. And climate change is the dominant driver of this change in northern regions, and land cover change can mitigate soil vulnerability in southern regions. So thank you for your attention, and I am happy to answer your questions if there is any.